In the previous live session, we saw that we need the bounce logic in order to filter all the input glitch on the input switch. So we have to design the bounce logic. Our bounce circuits is implemented with a counter and two flip-flop to avoid metastability. So when the input is high, the bounce counter counts, and when the counter reaches the bounce line, an output pulse is generated. So let's see how to simulate the bounce logic. We have the bounce test bench that instantiate our bounce component and generate an input pulse using a process. Here there is in line 40 and 41 there is the generation of reset and clock. Note that I need to initialize the clock signal in order to make clock less than equal not clock after 5 nanoseconds. That generate a clock of 10 nanoseconds of period. So let's start and simulate. We need to set directory. You have to use lab 3. So create library and use the script to simulate. In this case, we have to compile and simulate. No view opt is used to tell the simulator to not optimize the test bench file, because if you optimize the test bench file, all the signals not used in the test bench are removed by the simulator, and you can't simulate the test bench. So this no view opt constraint should be inserted in the test bench simulation. Then we recall a wave file that we saved in a previous simulation and start simulation. In order to change the input strobe, we use a counter, 8-bit counter that counts +1, and a selector that select a bit of this counter as input strobe. So we can see that if our input strobe is less than the bounce logic, so zooming in this case counter counts 1, 2 clock cycle, 1, strobe is 1, 1 and 2, output pulse is 0. No output pulse is generated. When? Because our debounce logic filter all the strobe less than 15 clock cycle. In this case, the input strobe is 17 clock cycle. In fact, the bounce logic generates a pulse. To instantiate the bounce logic into top level, I mean, we need to put the bounce logic here. So open up the top level, and as you can see, we put the bounce component here, and connect this point as input and take a GPIO1 D0 debounced as input of the OR. Here. As debug feature, we can use LED2 to see the debounced input. So let's lay out our design. Start Quartus 2 and generate new project. Set folder, create layout folder, and set the folder. Then the project is the top level. Add the files. And set the FPGA. Finished. At this point, we can close the project and set the pinout. So go to QSF. Okay. And add the pinout provided. Here. You can set also the pull-up resistor, copying the pull-up constraint from the previous project and pasting at the end. Save the QSF and reopen as a recent file. No, sorry. And reopen a recent project, the last project. Check in the assignment section if all the pins are okay. We can see the pull-up resistor on. Okay, and start simulation and start compilation. Okay. you can see technology map viewer, and you can see that we have all the module implemented into the FPGA as described here. We have the bounce logic, external button, or the edge detector, counter, and the driving of hexadecimal display. Now it's time to write your code. In the previous lab we designed the FPGA with edge detector, counter and segment driver. In this case we need to add the bounce logic at the manual switch input. So go in the lab3 folder, and in VHDL folder you will find 4 files: counter up, rising edge detector, the bounce VHD, and the top level DA0 FPGA. TB folder containing the simulation script. Open the file the bounce.vhd and complete the code in order to design the bounce logic. Simulate the bouncer, setting as a simulation folder lab3/vhd and create work library. Simulate the code in order to obtain the behavior of the live section. Then instantiate the bouncer on the FPGA top level and set the bounce length to 40 milliseconds. Remember that the clock board is 50 MHz. Lay out the code, and if you need help, you can find the solution in the lab 4. So let's program the FPGA with the bounced design. Turn on the board and start Quartus 2 programmer. Start programming and wait for programming. Okay, the FPGA is programmed, so we can see that we can drive with a push button. Now try to use, as you can see, we have a blinking LED, 2 blinking LED, one that blink fast and blink with all the input glitch detected, and the second one that blink once. In fact, the counter counts +1 because we are filtering all the bouncing less than 40 milliseconds.